Alright, so we are down to the last few days of Codevember this year, and I've been asking for a couple suggestions from people on Twitter. So David Langford suggested that we implement the Boyd's algorithm, which, if you're not familiar with it, it is a simple little algorithm that implements flocking behavior, which kind of simulates like birds or schools of fish. So for tonight, I don't think I'm going to exactly do that algorithm, but I wanted to try doing something similar. So the idea is we're going to have a bunch of particles on the screen. Whenever they update, they're going to look at some of their neighbors and determine some change in their own state based on the state of some of the neighboring particles. So let's go ahead and get started. Oh, hey Greg, welcome to the chat. Yeah, I did not realize when I started doing Codevember that I was going to end up streaming every day, but it ended up not being as hard as I imagined. But I will be glad to have a break once December gets here. Alright, so I have a new folder. I just ran elm-make to install our basic dependencies. And let's start our main.elm. So I want to use, again, Elm graphics. We used it yesterday and found we could get about 1,000 particles on the screen without too much of a performance problem. So I want to use that again. I think trying to use SVG would be even slower. We could maybe do something with OpenGL, or with WebGL, but that's a lot more boilerplate to get set up. So we want Evans CZ Elm graphics, and I also want to use the linear algebra package again, because it has some nice functions for vector math. And that is Elm Community / linear algebra. All right. And I'm kind of wondering if we should copy some code from yesterday. Let's pull it up and take a quick look at it. So yesterday we had our particle count, we had our model, an initial model, we had a separate particle class. So yeah, actually I think there's quite a bit of code here that is worth reusing. We had our message type, our update function, drawing. Yeah, alright. So I'm just going to copy this to start with. Let's see, we're also going to need the animation frame package. ElmLive animation frame. Okay. And let's see. Needs the particle module. So we'll copy that over to. Okay. So that looks like it all works. So let's start up Elm Reactor and load this up. Okay. So here's our sketch that we built yesterday. So let's go through the code and kind of rip out all the stuff for yesterday and start a new sketch, or basically a new definition for particles. Let's see. I'm going to pause that. Actually, let me bump down the particle count to 20. And then I can go ahead and let that run while I do this. Okay, so first of all, let's look at the model for our particles. So we're going to have position, and we're going to have velocity. What I'd like to try doing, so my idea for tonight is I want to have particles of different colors. So actually, I guess we should define that. And I guess I'll call it type. And for the moment, we'll just have a bool. So there's two possible types. We might change it to have more than two types later. So we'll have particles of different types, and on every update, each particle is going to look in some radius to find its nearest neighbors, and all of the neighbors within a certain radius, it's going to divide them into two groups, one for each type. And it'll move towards other particles of the opposite type and away from particles of its own type. So that's my thought, at least in my head. So I want to try implementing that, and we'll see how it ends up looking. So that means we're not going to need a velocity. And let's see. So what is format complaining about? Oh, the word type, I guess, is a keyword. Okay, so I guess we'll call it kind. And then update. For the moment, let's comment all of that out, and we'll just return the existing particle. And then random. We can use that, and then we'll need random.bool for our second parameter. Okay, so that's a good start for our particle module. And let's see what we need to fix up here. Alright, so our initial model, we can leave empty because we already have code to initially generate a set of random particles, and then also if particles go off the screen, it'll generate new random particles. So we don't actually need any to start with. Then what else is wrong here? So there is no velocity. So instead of drawing a little line segment based on the velocity, I'd like to just draw a circle. And it'll be a small circle with like radius 3. And we will collage.filled, I think it is, with a color. And we can use the let statement to make the color. We'll say if particle.kind, then color.black, otherwise color.white. And then we'll fill it with the color, and then we will move it to the particle position. Okay. Great. So that compiles. Let's see what we ended up with. And I do not want a blue background. Where's our background? Here it is. I guess what I was imagining was kind of like a sand color. We'd have like intelligent, a swarm of intelligent grains of sand or something like that. So let's kind of have a nice beachy background. So what is this? HSL 42, 73, and 66. And we did something yesterday where the background color changes over time. I'll just leave that out for now. Okay, cool. That is a decent start. Okay, so what's next? So what I'd like to do next is, I guess it's time to start implementing the algorithm here for update. So I was thinking there are two ways to do this. So every particle is going to depend on neighboring particles. So kind of the most straightforward way to do that is when we update each particle, we'll just go through the list of all the particles and find the ones that are near enough to be neighbors. I think that'll work. I'm not sure how quickly the performance of that is going to get terrible, because the time complexity for that is basically O of n squared. I was thinking a potentially faster way to handle that would be if every time we do an update, we first do an initial pass and go through each of the particles and insert them into a dictionary for every particle that they're near to. And then we would have a faster lookup as we go in and update each particle, but there would be kind of a longer starting pass to start out with. So that would be, I think the initial pass would be like O of n times some number, which is going to be the average number of particles that are within range of a given particle. So that'll be a constant. Yeah, I think that would be better performance, at least for a large number of particles. So we might want to implement that, but let's keep that in mind and see which is going to be the simplest to write here. So we're going to have an update. This takes a time and a delta time. I think we don't actually need the delta time in here. And yesterday we used the t to kind of have some varying random noise. I think we're not going to need that either. Let's just take the particle for the moment. And where is update? That's here. Okay. And I think the way I want to write this is to have this just take in a list of particles. And this will be the neighbors. And we will determine the neighbors outside of this function. We might want to write a helper function to do it. But we'll do the determination of neighbors from the outside. And actually, I think what we can do to start with is just consider all the particles to be neighbors. And since we have a small number, yeah, I think actually that'll be great for debugging. And then we can delay that decision I was just talking about which performance characteristics we want from our update passes. So let's see. So the goal here is we want to take the neighbors and divide them into groups. So we can have, or for this we can use list.partition, which takes a predicate and a list and divides this list into two lists, one of which for which the predicate is true and the other for which it's false. So if each of these are particles, we can just use .kind to get our Boolean out. And then we'll get a tuple of lists. We will get true neighbors and false neighbors. And actually what we want is we want to know the matching neighbors and the opposite neighbors. Maybe we'll call this same instead of matching. So this will actually be, we'll take the kind of the neighbor, and if it's equal to the kind of ourself, then it'll return true and it'll get into this first group, otherwise it'll get into the second group. Okay, great. So let's start with just a simple version of this. So let's try to take all of the neighbors that are the opposite color. Hey Albert, welcome to the chat. How's it going? Okay, so we have our particle and our list of neighbors. We find all the neighbors that are the opposite color. And then what I want to do is find the average position of all of those neighbors. So I think to do that, we can just add up all of the position vectors and then divide by the number. I think averaging vectors should work the same way as it works for scalars. So to do that, I'm not sure what to call this yet, but we're going to do a list.foldL, and we are going to take each neighbor and the accumulator, I guess let's call it sum, and we are going to, let's see, the sum is going to be a vector 2 of 0, 0, and we're going to be folding over the neighbors of the opposite color. And for each neighbor, we're going to have our current sum vector, and we are going to add, which is from the linear algebra math vector 2 package. We're going to add n.position to the sum. And actually we can curry this since sum is the last argument. Not sure if that's unnecessarily confusing to curry that or not. And then once we get that sum, we want to divide. So since it's a vector, we need to scale it, and we will divide by the number of opposite neighbors. So that's list.length opposite neighbors, and we'll probably have to float that. Okay, so this is the average, or this is like the center of the cluster of opposite neighbors. And, okay, so we have that. Then what I want to do is have the particle move one step towards that opposite center. So we'll take our particle and we'll set its position, change the position to equal particle.position, and then we'll add to that the normalized vector. So we want to take this opposite center, and we'll get a vector that points in that direction. Let's see. I guess we need this then. The direction from B to A. Okay, so we want to say direction of the opposite center from our particle's current position. And then we'll add that normalized direction vector to our particle position. All right, we've gone a long time without running this code, so let's run it and see what happens. Okay. So our particles are moving around. I guess that's working all right. Okay. So let's bump up the number of particles to 100. And, okay. So I think this is starting to look all right. So the problem that we have at the moment is that we are currently taking the average of every particle when we're determining where to move. And also, I guess I'm noting that the particles are always moving left. Oh no, I guess they start moving right. Okay, I'm not entirely sure that we implemented the algorithm correctly, but I think the next most important thing is, rather than considering all the particles everywhere neighbors, we want to filter down to just particles that are within a certain radius. So let's try doing that here. And let's do our slow algorithm first. So that means in here, in this lambda, where we have our particle, what we'd like to do is not pass all the particles, but filter the ones that are close. So this is the neighbor, and we want to find just the particles that are within a certain distance. So we'll say distance, let's see, and there is something called distance, right? The distance between two vectors. Okay. So the distance of between the neighbor position and the particle position, if it's less than some amount, say 100, then we'll keep it in the list of neighbors and pass it through. All right, let's see how this works. Interesting. Okay. So I guess I'm not sure, like this is behaving a little bit differently than I expected, but that's not to say we implemented it wrong. I think what I'd like to do is try hard coding a couple specific particles and see if those particles behave the way we expect. So let's see. So if we have, let's just add two particles to start with. We are going to have one particle, which will be at position -10, 0, and its color will be true. And we'll have another particle, which will be at 10, 0, and its color will be false. That 2, okay. And then let's disable the new particles command. We will have this just return the model. Okay. Oh, and we also want to disable the add particles. That'll also just return model. Okay, that was interesting. So let's check out what happened here. So we saw the two particles, and Let's see, what's going on in their position? Okay, and you can see the position. They keep moving closer to each other. And then they're at 0, 0, and then the particles get filtered out. Let's see, so is particle.inbounds not working properly? Let's console.log, or debug.log. And then we will also debug this. And let me pull this up here. Oh, I see. We are eventually, I guess, having no particles, or I guess we're dividing by 0, I would guess. Let's see, opposite neighbors. Well, we should. Debug.log, let's debug here too. So neighbors is all the true ones are at 0, 0, all the false ones are at 0, 0, and then at that point, our new position, oh, okay, so direction from one number to itself is giving like a division by 0, essentially. Okay, so let's fix that, and I guess we'll say if opposite center equals, we can do this here, if opposite center equals particle position, and actually let's add another variable, target position equals opposite center for now. And if the target position equals our current position, then we'll just return our particle. Otherwise, we will return all this stuff. Okay, so that should fix that problem of the particles disappearing. Okay, so they're staying there. So that seemed correct. Let's add another false particle. So let's put this one at like 20, 10. Okay. So the black particle moves towards the center location of the two white particles. Okay. And then the white particles just follow after it. I guess we'll, oh, interesting. And then they come back to the center. I guess because there's no neighbors for them to follow. Okay. So let's do this. I'd also like to calculate the center of the same particles, or the matching particles. This is going to be basically using the same calculation, just with the same neighbors instead. And then our target position is going to be the average of the opposite center and the negative direction of the same center. Opposite center, and we're adding to that math.vector 2.negate. Okay. Well, this seems a bit more interesting. Yeah, okay. So I actually like how that's looking. I think the other thing I'd like to do is make it so that not all of the particles move every time. And I guess I'm not sure of the best way to do that. I guess we could produce like a random list of particles to generate. I guess we also could just like have a step number and loop through that. Let's try doing that. We'll have an I, which will be an integer. We'll start that at 0. Every time we update, we will increment I. Then we're going to, let's see, do an if statement in here. So I guess we need to make this an indexed map. And we'll say, then we'll get an I in here. We'll say if I mod whatever, 5, so let's say 5 different groups equals, and let's see, I'm not sure of the operator precedence, so I'll put these in parens, model.I mod 5, then we'll update, and if it's not, then we'll just return the particle. Okay, so what I'm expecting this to do is this will just update every 5th particle, but then every time we do a step, we're going to increment this, so we'll shift through sets of particles. So every 5th frame, every particle should update. Yeah, well, it looks like that is working, although it like the visual effect of that is just that everything looks kind of slow and stuttery. Let's try doing larger groups. Because I guess this also means that we can increase the number of particles as well, since we're not doing as much updating every time. Well, we can't do that many. Yeah, okay. That was a nice idea, but I don't think it's really working out that well. Yeah. All right. Well, I guess that's going to be it for tonight. I am going to leave it here. I think we did pretty well for just making up an artificial life algorithm on the fly. And actually, when we did yesterday's with the deep sea particles, I actually wasn't too happy when we first finished with it, but after I was watching it later, I have been enjoying it more and more as I've looked back on it. So, yeah, in any case, the same kind of setup could be used to implement the Boyd's algorithm. I don't have it up anymore, but the Boyd's algorithm does something very similar, but it also tracks the velocity and the direction that the neighboring particles are facing. So we basically have it set up. All we'd have to do is change the update function in our particle module to calculate changes differently. So yeah, thanks for tuning in on the penultimate day of Codevember 2016. So there's one more day left. If you have some good ideas of what I should make tomorrow, let me know on Twitter. And yeah, I guess that's all I have to say for tonight. So I will see you all around. Have a great night.